Continuing our discussion about turning points, let's talk about local versus absolute maximums and minimums. So I mentioned this a moment ago in a previous video, but let's give you a full definition. So if a function has a local maximum point that also happens to be the highest point on the graph of the function overall, it is called the function's absolute max. So for an example, take a look at this graph. So I have a turning point right here. I also have a turning point here and a turning point here. This is a maximum. But this point is an absolute maximum. Now it's also a local max. It's both. Okay. So if you understand that concept, it's easy enough to transfer that to thinking about a local minimum. So let's talk about, while we have this picture up, what are the local minimums? So right here, we have a local min. And then, what else? Well, we don't really have any other local minimums. And in fact, the function continues to go down, and it continues to go down over here on both the left and the right directions. So actually, this function does not have an absolute minimum. So we have a local minimum, but not an absolute minimum, whereas we do have an absolute maximum and two local maximums. So that gives you an idea of some of the variations you might see in terms of local maxes and mins. Here's the official definition for an absolute minimum. Here's another example. We have a local minimum, which is an absolute minimum. It occurs at the point 2, 0. This function does not have a local max. What about this function? Well, we have one local and absolute minimum. We have no local maxes. The function's decreasing here and increasing here. Specifically, it's decreasing from negative infinity up to 5. And notice I used a parentheses here for negative infinity, because negative infinity is not a number in the sense that the integers are numbers. So it's decreasing from negative infinity to 5, constant nowhere, and increasing from 5 bracket to positive infinity parentheses. I'm sort of doing this in backwards order, but let's also identify the domain and the range. The domain of this function is all real numbers. And the reason for that, and again this is parentheses, is we can assume that this behavior continues as we move to the left and to the right. And as you go to negative infinity, you will always have an input that gives you an output. And as we go to positive infinity, I can put in any large number and I can get an output. Therefore, my domain will be all real numbers. My range is somewhat limited. It begins at 0 and then goes up from there. And I'm just getting this purely by inspection of the picture. All right. I've got some more examples here of increasing, decreasing turning points. I encourage you to take some time to look through these as you read through the notes. All right. So having discussed what it means to be an increasing function, a decreasing function, or a constant function, we're now going to bring in a somewhat deeper function characteristic. And this slide that you see now is sort of a first pass at that. And really what this new function characteristic is about rate. Rate. And rate, you can sort of think of that as like velocity, if that helps. Let's look at this picture. So what you've got here is a line, right? This is an increasing line. And its rate of increase is constant. Now, let's just sort of think of this kind of on an intuitive level. The idea of constant rate means that it never gets any steeper. The steepness from here to here is the same as the steepness from here to here. So if and we can quantify this by thinking about rise over run. The run here and the rise is the same as if I go the same run and the same rise. So the steepness is constant. Now, if the steepness, just to give you a quick idea of a picture that whose steepness is not constant, let's look at that. So this is not constant steepness. Now the function's increasing, but we've got somehow have this difference in steepness, and we want to kind of name that. All right. So moving along, we could also look at a decreasing function. Notice a decreasing function has the same characteristic that it's or this decreasing linear function, I should say, has the same characteristic that it's decreasing at a constant rate. So linear means constant rate as we move from left to right and for a decreasing function. Okay. And similarly, if I did something like that, I'm still decreasing, but not linear, not constant rate. So these pictures that I'm sketching over to the side that have non-constant rates, let's dive into that a bit more. There's a special name for those, and that sort of behavior is called concavity. So concavity is basically when we're looking at functions that increase or decrease at non-constant rates. They have concavity, they curve, okay? And we have different types of concavity. The first kind is what we call concave up. So concave up means that the function bends upward. So let me sketch a picture of concave up functions. Here is concave up. And here is also concave up. If you glue these two together, you'd have something like that. And there you kind of get the idea of what we mean by saying that it holds water. So this is concave up and increasing. This is concave up and decreasing. Now, what does it mean to be concave down? Well, it bends downward. So let's think of all the ways that we could bend downward. Well, we could do this. We could do this. Or we could kind of glue these two together and do that. So these are three examples of concave down functions. This is a decreasing concave down. This is an increasing and concave down. This one both increases and decreases and is concave down. So concavity, what is it about? Well, it's about describing the rate at which a function changes. And I want to make sure that you differentiate that from increasing and decreasing. That's about, it's not about the curvature of the function. Concavity is about how the function curves. I'm going to run now through several pictures where we go into this idea a bit more. Here's increasing and concave up. So another way of describing this is we say the function is increasing at an increasing rate. So the rate of increase grows. And just to we can actually quantify this increasing rate. Let me say this: the rate is growing towards positive infinity. So the rate, how steep it is as we move further over, is going towards positive infinity. Now the function itself is also increasing. This is concave up. Increasing concave down function, on the other hand, we would say is increasing at a decreasing rate. And a decreasing rate means that the rate is approaching 0. So it's flattening out. Similarly, with a decreasing function, again, when we are flattening out, the rate is approaching 0. Okay. And when we are decreasing and concave down, and this one is always, I think people sometimes get confused about this, but we still say this is decreasing at an increasing rate because the rate is approaching negative infinity. Now, when I say approaching, I'm not saying that it's going to get to negative infinity. I just mean it's moving in that direction. It's moving away from 0 and towards negative infinity. And you might say, well, how is that increasing? Isn't that getting smaller? Well, it's increasing in magnitude. Like negative 100 has a bigger magnitude than negative 50. Now they're both negative numbers, but one is further away from 0 than the other. Just as we talked about turning points being points where we change from increasing to decreasing behavior, we can also talk about inflection points. Inflection points are points where we have a change in concavity. So in this picture below, you see a graph that goes from concave up, and then it has this sort of point right here where it switches from concave up to concave down, and that point is an inflection point. And inflection points are sort of harder to see because they don't correspond to peaks. Like that right there, that's a turning point, not an inflection point. Notice with an inflection point, we're still increasing when we move through it. So the function's increasing here and still increasing here. It's just increasing in a different fashion. Similarly over here, in a decreasing function, you're still decreasing in this region. We're decreasing on each side of the inflection point. It's just that on one side we're concave down and on the other side we're concave up. Okay, so to recap, we have inflection points that are keyed to concavity, and turning points are keyed to increasing, decreasing, and constant behavior. And that wraps up section 2.2.